Now, let me help you out in this question. There is a circular coil of wire consisting of 100 turns, right? So the number of turns you know. Each of radius 8 centimeters. So in this case, 8 centimeters should be converted to meter. Okay. It is carrying a current of 0.4 ampere. What is the magnitude of magnetic field at the center of the coil? Remember, for the case of a circular coil, I am talking about this diagram. For this case, we were just found the magnetic field on the axis of it, right? At this point, we are just able to find out the magnetic field. So, for this case, what we had done, that if the current was passing through that of circular loop in the form of I, so that small portion is about what? It is of IDL. This is the current element. So for the current element, we were just able to find out the magnetic field at this point. I hope everyone remembers the diagram where there was an angle that is equals to phi, and for that case the magnetic field at the center the magnetic field was mu naught Ni divided by of 2a, right? Actually, we had a very long expression. In that case, you have to just substitute. If that was x, if that portion was a, and this is what r, just substitute in that long expression x equals to 0. I'm just writing down that long expression what we had got. Actually, let me write it down, then you will be just able to understand that one better. That is the magnetic field for that case, that is of mu naught n I, sorry, mu naught n I a square divided by of 2 into a square plus of x square whole to the power of 3 by 2. We have just got this big expression. Now in that case, if you just substitute x equals to 0, what you will just get in this case, after substituting x equals to 0, that is the magnetic field at the center of the coil, what will be the value of it? That is of mu naught in I divided by of 2a. So you have to just substitute all the values in this. So the number of turns is equals to 100. In this case, the radius that is of 8 centimeter, it is equals to 0.08 meter, and the current that is passing of 0.4 ampere. All the things I have just written on one of the corner. Yes, you have to convert that centimeter to meter, that I have converted every time. For the previous case also, even for this case, every time when the radius is given in centimeter, you have to convert it to meter. So in this case, all the things which are given in this question, we have to note it down first. So the number of turns is 100, the radius that is equals to 0.08 meter, the current that is of 0.4 ampere. Now we have to just substitute all these values in the mathematical expression of magnetic field, that is of mu naught Ni divided by of 2a, right? So when we are substituting, let's see what the value we are just getting over here, right? In this case, I have just written a, but this is actually the radius. In this case, you can write down this is actually the radius of that. So a is equals to 8 centimeter, and you can say it is about 0.08 meter, right? So now in the next page, I'm just going to substitute all of the values, where a is the radius of the circular loop, n is the number of turns, and I is the current flowing through that of circular loop. Okay, so what the value of b we are just getting over here, the b is equals to mu naught Ni divided by of 2a. So mu naught is having the value of 4 pi into 10 to the power of minus 7. Number of turns, that is equals to 100. The current is about how much? The current is about 0.4 ampere, right? So it is 0.4 divided by twice of the radius. Radius is how much? Radius is 0.08 meter, right? So I am just substituting that value as 0.08 meter, right? Now we have to just calculate that one. For that case, 0.4, and if we just eliminate this, it will be of 0.2. And now we can say that this will be of 4 pi into 10 to the power of how much? This is 10 to the power minus 7. This is of 100. 100 means 10 to the power 2, right? So I can get this is of 10 to the power minus 5, and in this case this is of 0.4. So now how much you can get that by the simplest form of the calculation, that will be this is of 10 to the power minus 1. So if it is goes up, it will be of 10 to the power minus 4, and we are getting pi into 10 to the power of minus 4. I found 3 point, yeah, that's the correct answer. Pi means that is of 3.14 into 10 to the power of minus 4, that Tesla. That's very good. You have found the answer. Right? In this way, we have to just proceed for the calculation. Right? Now, whether the solution is understandable, everyone? Okay, that's very good. Now we are just proceeding to the next one. That is, we can proceed for the next question. Actually, we have got the solution for the case of Ampere's circular law, even for the circular loop also. Right? Now, I'm just giving you one question. Let's see who can able to solve that. Okay? This is again the application of Ampere's circular law, but let's see whether you are able to solve or not. So a closely wound solenoid, a closely wound solenoid 80 centimeter long has a has five layers of windings of 400 turns each. 400 turns each. Okay. The diameter of the solenoid is 1.8. The diameter of the solenoid is 1.8 meter each. Find the magnetic field inside the solenoid. Find the magnetic field. Remember one thing, when it is asked for the case of solenoid, you have to find the magnetic field. You will only get the magnetic field inside of the solenoid. Okay, so I'm just writing find the magnetic field inside the solenoid. Outside of the solenoid, the magnetic field is 0. So only the magnetic field we are getting inside of the solenoid. Please write down the question at first. A closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 meter. Find the magnetic field inside the solenoid. Sorry. So whether the question is written, everyone? Don't take the screenshot if anyone is taking. Just write the question carefully. Then you will be able to solve that. Okay. So a closely wound solenoid 80 centimeter long has 5 layers of windings of 400 turns each. The diameter of the solenoid is 1.8 meter each, right? So what the things are given in this question, at first we need to write it down, right? So what the things are given in this question, that is the number of turns. So in this case, the number of turns we have to write it down. Let me change the ink of that. So the number of turns, how many number of turns are there? That is of 5 layers. It is having a 5 layers of windings of 400 turns each. So what will be the total number of turns? That is the number of layers multiplied by number of turns in each winding. That is equals to 2000 number of turns, right? So 2000 total number of turns we have just found here. Now in this case, the current, what is the value of the current? The diameter of the solenoid, it is given. Oh, the current I have not given now. So in this case, just write it down. One information is missed by me. If the current carried is 8 ampere, this small information is missed by me. Now in this case, when they have asked to find out the value, 2.5 into 10 to the power minus 2. Okay, okay, but in this case I have not mentioned about the current, I think. Okay, you have just got that answer. Let's see whether we are getting the same answer or not. So in this case, the current carried, that is of 8 ampere. So I is equals to 8 ampere. Now, so a closely wound solenoid 80 centimeter long has the 5 layers of winding. So total number of turns we have just found as 2000. The current carried by it, that is of 8 ampere, right? So in this case, that is, what is the length of that? That is of 80 centimeters. So we can say this is of 0.8 meter. Now we are just going to, now we are just going to substitute all the values in the mathematical expression of the solenoid. So for the case of solenoid, what we know, that the magnetic field inside the solenoid, it should be mu naught multiplied by n multiplied by the I, right? So in this case, what is small n? The small n is the number of turns per unit length. Okay, small n is the number of turns per unit length. So it can be written as mu naught multiplied by total number of turns divided by total length multiplied by I. Right? I'm just telling you again, small n and capital N both are different. Small n is actually the number of turns per unit length. So I have written that small n equals to total number of turns by total length. Okay, so it is equals to mu naught is having the value of 4 pi into 10 to the power minus 7. Number of turns is about 2000. Current is about 8 ampere, and in this case the length, that is of 0.8, right? So after the calculation, yes, that is of, we are getting how much? That after the calculation, that is of, if we are cutting this 8, we are getting here 0.1, that will be of 20,000. 4 2s are 8 pi. 8 pi means 8 into 3.14. 3.14 into 8, that is of how much? For the 32. Okay, that is, we are getting approximately same of your answer, 8. That is of, even we not multiply also, we will get the answer as 8 pi into 10 to the power of minus 2 Tesla, right? So we are just getting the same answer, that is of 8 pi. If you just do the calculation also, it will be of 2.5 into 10 to the power minus 2. Actually this is your book's problem, so that's why you are able to answer that clearly. So whether the solution is understandable, everyone? Just give me a quick fast reply. If you not understand, then please tell me. Okay, that's very good. Now, whatever the problems we have just discussed up to that, we are just discussing the next problem. Then we'll proceed for the concept, right? So now, rest of the people, whether you have written that solution, Antinaro, Pongmai, Dipti, Catherine. Now, those people who are not able to join our class, they will just get the recording because we have just started that. Explain the last line once again. Sure, I can explain the last line. Let me move to the next slide. Okay. No, I'm just erasing that portion and I'm just right again over here. So actually, we are just going to find out the magnetic field for the case of solenoid, right? Wait, just wait. I'm just erasing that portion. So for the case of solenoid, we'll be just getting the magnetic field inside of that. So solenoid is look like that, like it is in the form of solenoid, some cylindrical were like that, they are wound like that. So in that case we'll just get the value of the magnetic field inside of the solenoid, like in this portion you will just get the magnetic field. So the magnetic field is having the expression of mu naught multiplied by n multiplied by I. So here n is the number of turns per unit length, right? N is the number of turns per unit length. So whatever I have just written, so n is equals to total number of turns divided by total length, right? So it can be written like that. So I can modify the formula. So it is equals to mu naught multiplied by of n by of L multiplied by of I. Sorry, just move to the next slide. So mu naught multiplied by of n by L multiplied by of I. So that thing we can write it down, right? So now whatever the value of magnetic field we have just got like that, so if you just substitute all the values in that mathematical expression, you will just get everything. Okay, so in the next page I'm just going to substitute everything, that means all the values. That's b equals to mu naught multiplied by of n by L multiplied by of I. So mu naught is having the value of 4 pi into 10 to the power of minus 7. Total number of turns is equals to 2000, and in this case the current is of 8 ampere, and the length is equals to how much? That is of 0.8, right? In this case we have got the length as 0.8, so it will be of 0.8. So if you just do the calculation, it will be of 0.1. That means if you omit the point, it will be a 0 again here. That will be of 8 pi into 10 to the power of 8 pi into 10 to the power of 1 2 3 4, that is of 10 to the power minus 3 we are getting. Thank God we have just got the answer like that. If we just do the calculation, that is of 8 into 3.14 and it is of 10 to the power minus 3, you will just get the value. That is of 8 4 is of 32, 8 3 that is of 11, that is of 25.12 into 10 to the power minus 3, that Tesla, and we will get as 2.512 into 10 to the power minus 2 Tesla, right? In this way the answer will be. Okay, now we are just moving to the next problem. That problem I have just told you for the case of the helical path of a magnetic field, right? That means when a charged particles just moved in a magnetic field, it just moved in a helical path, in a circular loop, right? So for a circular loop, if a charged particle is entering into a magnetic field, so some magnetic force will be experienced by that charged particle, right? So we have to find out the, we have just got the expression for the radius of that helical path. That means if a charged particle, suppose this is the magnetic field, and if a charged particle is entering, there is a charged particle who is entering in that magnetic field, so it will move in that of helical path. In that of helical path, it will just continuous to be moved because some magnetic force is experienced by the charged particle. So in that case, that helical path should have some radius. So the radius of a helical path, that is of mv by of qb. I have just told you about that, right? Because if it is moving in that of circular loop, in that of helical path, some magnetic force is being experienced by the charged particle. The force experienced by the charged particle is equals to mv square by r. This is the centripetal force is experienced by the charged particle, where the radius of the circular loop, it is of mv by of qb. So with respect to that concept, I'm just giving you one question because we have seen that in the year of 2017, 18 and 19, that kind of question is being asked. So that's why I'm just giving you. So now the next question I'm just giving you, this is the last question, then we'll move for the concept. Okay. So this is, I think, question number 4 or 3. Let's give it question number 4. So in a chamber of uniform magnetic field, of 6.5 Gauss. Gauss is the CGS unit of magnetic field. 1 Gauss 1 Gauss equals to 10 to the power minus 4 Tesla. That is given in the question. Okay, you should know about that also. Is maintained. Okay, so an electron is short. An electron who is entering in that field. That means an electron is short into the field. Into the field with a speed of 4.8 into 10 to the power 10 to the power 6 meter per second. Okay, normal to the field it is entering. Determine the radius of the circular orbit, right? Now everything you know in this case. Now if an electron is entering into that of magnetic field, it can be a uniform magnetic field or non-uniform magnetic field. It will try to move in a helical path in a circular loop. So one question is asked here, explain why the path of an electron is a circle. Because the magnetic force is experienced by the electron, so that's why it is, the electron is bound to change its direction of motion every time. So that's why it is moving in a circular path. Because if you are moving in a circular path, you are changing your direction of motion every time. So that's why the path of the electron is circular in nature. So in this case, what are the things are given in this question? At first write it down, then find out the, just use the mathematical expression to find out the radius of the circular orbit. At first write down the question, everyone. Now have you written that question? Girls, do you have written that question? Should I proceed for the solution?
Yes, sir.
Okay. Now, the radius of the orbit, that is equals to m into v divided by of q into b. We know that relation. So in this case, the electron is moving. So in this case, I will write down the q as this is of m into v divided by of e into b, right? So what is the mass of an electron? The mass of an electron, that is of 9.1 into 10 to the power of minus 31 kg, right? And the charge of an electron, that is a 1.6 into 10 to the power minus 19 coulomb. You know that values. So in that case, we are just going to substitute all the values over here. That mass is equals to 9.1 into 10 to the power minus 31. Velocity, it is having the velocity of how much? That is of 4.8 into 10 to the power 6, right? So 4.8 into 10 to the power 6 divided by 1.6 into 10 to the power minus 19 coulomb multiplied by the magnetic field. Magnetic field is having the value of 6.5 Gauss. 1 Gauss is equals to 10 to the power minus 4 Tesla. So it will be of 6.5 into 10 to the power minus 4. So now we have to just do the calculation. Now for the ease of calculation, what I believe that I should separate them like that. It is of 9.1 multiplied by 4.8 divided by 1.6 into 6.5 multiplied by 10 to the power minus 31 and 10 to the power 6, that is of 10 to the power minus 25 divided by 10 to the power minus 10 to the power minus 19 and 10 to the power minus 4, that is of 10 to the power minus 23, right? So finally we are getting 10 to the power minus 2, and here after the calculation what we will get? 9.1 into 4.8 divided by 1.6 into 6.5. Just tell me what we will getting. After all the calculation, whether anyone is telling the answer, everyone, that is of 9.1 into 4.8 divided by 1.6 into 6.5. 9.1 into 4.8, that is the 43.68 divided by of 1.6 into 6.5. So 43.68 divided by of 1.6 multiplied by of 6.5. So we are getting as 4.2, right? Okay. So in this case, we are getting the final answer as 4.2 into 10 to the power of minus 2, that meter. So you can say the radius of the orbit, that is of 4.2 centimeter, right? So when the electron is entering into that of magnetic field, some magnetic force is experienced by that, right? So after getting the force, it is just moved into a helical path. So the radius of the path we are getting as 4.2 centimeter. This is the final answer. So whether the solution is understandable, everyone? Just give me a small reply. And Fidolin, okay, I'm not getting it. Whether you are understanding that concept, just tell me that whether the concept is understandable. when a charged particle is entering into that of magnetic field. Oh, you are getting stick with the calculations. So in that case, there is only one way, that you just omit the points here. You just omit the points like that. So now it will be easy. That is of 91 into 48 divided by 16 into 65. Just do the approximate value in the above, in the numerator portion. Just assume it is of 90 into 50. In the denominator, just assume it is of 16 multiplied by of 65. That's same. After doing the calculation, it will be easy for you. Okay, just proceed with the approximate values. Actually, I do that in that case, that it is of 90 multiplied by of 50 divided by 16 multiplied by of 65. So you are getting the approximately correct answer. Don't worry. So okay, so rest of the people, whether you are able to understand that concept. So we are just moving to some of the theoretical part. Okay, that's good. Now, what the theoretical part that we had actually last time covered when only Kunzani were in the class. Okay, so in that case, we had just covered some of the topics, that the radius of the circular path that been covered in that time also. Okay, so in that case, we are just covering it again. Don't worry for that. Okay, now if there is some magnetic field, if there is some magnetic field, and if a charged particle, suppose the electron, in this case I'm just assuming it is not an electron, it is a positively charged particle who is having the charge of q, who is entering into that of magnetic field with some angle. That means I just want to draw the diagram like that, that it is a uniform magnetic field, and the charged particle is entering the magnetic field is like that. In this way, the charged particle is entering. This is having a charge of plus q, and the magnetic field is like that. So in this case, some magnetic force will be experienced by that. So what will be the value of the magnetic force that will be experienced by on the charged particle? That will be a perpendicular with respect to its motion. That means it should be like that. So the magnetic force will be experienced by that charged particle. It is having the mathematical expression as q multiplied by of v cross of b, right? So this is the mathematical expression of the force experienced by the charged particle. This is the magnetic force experienced by the charged particle. So it can be simplified as q vb sine theta, because in this case you are able to see that there is an angle with respect to the magnetic field. The charged particle is having some angle with respect to the magnetic field, that is of theta. So that's why when it is entering into that of magnetic field, the magnetic force which is experienced by the charged particle, which is perpendicular with respect to its motion, we can say, right? So here we can say that the mathematical expression that is of qvb sine theta, right? So what is the motion of a charged particle in different conditions? Because in this case we have just assumed that the charged particle is entering the magnetic field with some angle of theta. Now if in case 1, we'll just write it down, that if the magnetic field is like that, and if the charged particle enters like that, that this is the motion of the charged particle, that means it is having some velocity of v. This is the charged particle q, and this is the magnetic field. So in that case, what you can see, that the charged particle have entered into the magnetic field, and the angle between the motion, that's the velocity, and the magnetic field, that is equals to 0. So when the angle between the velocity vector and the magnetic field, that is equals to 0, so theta is equals to 0, so no magnetic force will be experienced by the charged particle. So what can I conclude? that if the charged particle is entering into the magnetic field parallel to that of magnetic field, so no magnetic force will be experienced by it, because in this case whatever the angle we'll be considering, that is with respect to that of velocity vector and the magnetic field. In the previous case also, this is the velocity vector and this is the magnetic field, so angle between the velocity vector and the magnetic field is theta, so that's why we can say this is of VV sine theta. Okay, so if the particle is entering into that of magnetic field parallel with respect to that, so the angle will be 0, so no magnetic force will be experienced by the charged particle, so the force will also be equals to 0, right? Now I'm just moving to the next case, that suppose we are just assuming that there is some magnetic field. Okay, the magnetic field is represented by the cross, right? That means the magnetic field is in downward direction, I can say like that. Now in that magnetic field, this is a uniform magnetic field actually, perpendicular to the respect of plane. Now in this case, if the charged particle is entering into that of magnetic field with some velocity, if the charged particle is entering in that way, suppose in that way if the charged particle is entering into that of magnetic field, this is the charged particle and this is the velocity of the charged particle. So when the charged particle will enter into that of magnetic field, the magnetic field is working in the downward direction and it is entering into that of magnetic field, so it is entering perpendicular with respect to that of magnetic field. So when it is entering, it will try to move itself in a circular path, so it will move like that. So the direction of the charged particle can be determined by drawing a tangent like that. At any of the point, if you want to determine the direction of motion of charged particle, you just simply draw a tangent. So this tangent will show the direction of its motion. That means it can be denoted as a velocity vector, right? So in this case, the force is experienced like that, to the perpendicular of its motion. For each and every case, you will say that the force experienced by the charged particle when it is entering into that of magnetic field, that is perpendicular force is experiencing by the charged particle, right? Just visualize that portion, that if the magnetic field is in the downward direction and if some charged particle is entering into that, so obviously it is entering perpendicular with respect of magnetic field. So the magnetic force will be experienced by this, that can be represented by F, and it can be denoted like that, whatever the diagram I have just drawn over here. So it is of how much? This is of Q into V cross of B, right? But one another thing, that if it is continuous to be in rotation of that circular path, suppose if the charged particle is continuous to be in rotation in that circular path, so obviously some force is responsible for its motion. Which force is responsible? So magnetic force is responsible, right? So in this case, the magnetic force which is working towards the center of that circular path, right? The magnetic force in each and every case is acting towards the center of the circular path, so it's a centripetal force. So the centripetal force is having the value that is of mv square by r, right? We know that the magnetic that the centripetal force is having the value that is of mv square by r. Now that one, in this case, the angle between the velocity vector and the magnetic field, that is of 90 degree. So what can I write down? It is of qvb sine 90. So it is just only qvb. So in this case, whatever the magnetic force is experiencing by the charged particle, the force is acting towards the center. So it is a centripetal force. So the value of this centripetal force and this magnetic force will be equal. So the magnetic force is equals to the centripetal force which is working on the charged particle. So the V can be eliminated and the radius, that is of mv divided by of qb. Remember we had derived that expression in the last class. Now if the particle is continuous to be in motion, that means it is rotating in that circular orbit and its motion is continuous, so obviously it is having some kinetic energy. So what is the expression of the kinetic energy? That is equals to half mv square, right? So in that case the expression can be changed. This mass into velocity. Mass into velocity is how much? It is actually the momentum. So it can be written as P by QB, right? So in this case, if the kinetic energy of that particle, that can be represented as half mv square. So what can I write down with respect to that? That v square is equals to 2 into k divided by of m, right? So in that case the V will be equals to root over of 2k by m. Whether I can write down it that the velocity, which velocity is having the expression with respect to the kinetic energy in the form of like that V equals to root over of 2k by m. So what I will do, I will just substitute the value that is of root over of 2k by m in that expression. Okay, after substituting in that expression we'll get a new expression of the radius of that circular path. Okay, so up to that, whether everything is understandable, everyone? Guys, okay, thank you. Now we are just going to substitute that portion. Now whether you have written that, okay, you have written that, okay, that's good. Now I am just going to substitute that value, that is the radius of that helical path, that is you can say the circular path, because the motion of the charged particle in that of magnetic field which is continuous, that is of mb by qb. And what is the expression for v? That is equals to root over of 2k by m. So if I substitute that, it will be of root over of 2k by m and divided by of qb, so it will be of root over of 2km divided by of qb. This is a new expression, right? So you can write it down as root over of 2mk divided by of qb in that form also, right? Now if the particle is being accelerated, that means we have just applied a potential of v. If we apply some potential of v, suppose if a potential v is applied, if a potential v is applied, then what will happen? The kinetic energy, in this case the kinetic energy, that is equals to the charge multiplied by the potential. We know that expression. If you apply a potential of v, then in that case kinetic energy, that is equals to the charge multiplied by the potential. So in that case the radius, that is equals to how much? I can write down, it is of root over of 2mqv divided by of qb, right? So it will be of 1 by b will be of outside and it will be of 2mv divided by of q. So this expression is also for the radius of that helical path. That means you can say that the circular path. So for the radius we are having lot of expressions, right? One, we have substituted the value of the kinetic energy and we are getting one expression. Again, if you are applying some potential, then we are getting a relation of the kinetic energy with that of potential. That kinetic energy is equals to the charge multiplied by the potential. So after substituting, we are getting a new expression, that 1 by b equals 1 by b multiplied by of root over 2mv by q, right? Now the last portion. I hope that part is understandable, everyone. Whether it is written, girls, whether it is written. Okay, thank you. Now we are just moving to the last portion. That means the particle, how much time period is needed for the particle to complete one revolution. To complete one revolution, that means the time period is represented as total circumference of the circle, that is of 2 pi r divided by the velocity, right? So in this case, what can I write down? That r is having the expression r is equals to mv divided by of qb. So we can substitute that value in the place of r. So what I will get, that is of m into v divided by of q into v, and here actually one v was there. So v is getting eliminated, right? So we are getting as 2 pi m divided by of qb. This is the time period for one revolution. Okay, even the frequency, that is equals to 1 by time period, it can be found as qb by of 2 pi m. Okay, everyone, so in this case we have just found the time period as well as the frequency for the charge particle. So up to that, is there any doubt? Now, as we have missed a lot of portions, lot of class we have just missed actually. So now we have to study for the Lorentz force. The next topic of the class will be Lorentz force, the cyclotron. I will just tell you what is the machine the cyclotron is. So now we have to study the force applied on the charged particle. Sorry, in an electric and magnetic field for both. Now we'll study the parallel of that means the force between two parallel current carrying conductors. That's the last portion, and the magnetism first chapter will be finished. Second chapter is not actually total, the total portion is not on your syllabus. So the first chapter we will be completing in the next class. So up to that, is there any doubt, everyone? Okay, thank you. Now at this point I'm just ending the session as